Well, hello everyone, welcome back again. And like I said, I've been writing several database-related modules in the past 2 years, and I wanted to share some of that with you. And uh, 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 yes, in particular, one of my big projects of last year was Net Postgres, a new module for accessing Postgres databases. Now you may wonder, why is he writing a new Postgres module? There already is an excellent one. Well, this has one big reason and one small reason. The main reason why I wrote this was asynchronicity. See, DB Postgres is an excellent module for accessing the Postgres database. However, it is inherently synchronous, because libpq is inherently synchronous, I think, or at least the easy way to use it. And in a lot of cases, this is perfectly fine. This is not wrong, but in a lot of other cases, asynchronicity is very desirable, especially because the asynchronous support in Raku is one of our strong sides, and it feels a bit wasteful to use like an asynchronous web development framework and then combine it with a synchronous database module where you still have to wait, where you're still waiting for the database synchronously. The second reason why I wanted a new module is that I wanted better type mapping, which I'll get back on later. And how does one approach writing a module like this? The right way to write any kind of networking module, and yes, as you may notice, I have strong opinions on wrong and right ways here, is to do a very layered approach, where there's like a networking layer, a serialization, there's messaging, and there's logic. And serialization is, I think you all know what it means. It's really making sense out of bytes, being able to round trip things. And if you're lucky in writing a networking implementation of a networking protocol, you can reuse an existing framework. If you're writing your own thing, you should not reinvent the wheel. Absolutely not. If you're lucky, you can use something like protocol buffers, for example, or Swift, or there are many options here that you can use as a serialization framework, so that you don't have to write it yourself. However, I was not this lucky. Postgres does a custom thing for historical reasons. Therefore, I essentially first had to write my own implementation of these serialization concepts, so that I could write the serialization of the messages, the next step. The second layer are basically the messages in both directions, as they are sent from the client to the server and from the server to the client. These are very semantical meanings, and having these very explicitly split out is absolutely essential for writing a testable networking module. Because you see, once you have these two, you can test the serialization of these messages in both directions. You can see, are they round tripping? Are they being is a known message interpreted correctly? Are they written to the wire correctly? And this is the crucial first step of testing any networking implementation. And if you don't separate this out, you're gonna have a very hard time getting your implementation to be correct. Now, the next layer is the logic. Like, for example, if you do a query, what message, like it will send out certain messages. If it receives certain messages, it will respond to it in various ways. And if you have these messages and this logic, that means you can do like functionally test, how does this client, how does it work? in my particular example, I have a test suite where I have a test suite where I can test, like if I quit the exactly what is sent, how does it react when it gets this unusual reaction, without using any networking. And this is really important because networking is the absolute hell, is the hell of testing. Once you're dealing with networking, it stops being quite as reliable as it is without, but also it stops being as performant as it would be without, because there's always delays in there, and you always need some timeouts, because otherwise you can't see spurious failures, and you really want to test these things without each other. And also, because when you're separating this, you know for certain that if you see an error, is this a problem in like the serial? If you don't separate this, you don't know, is this a serialization problem or is this a logical problem? Whereas if you have these separated, you can very easily debug these. And like I said, I have protocol Postgres and net Postgres, because this is the last step, the fourth layer, actually finally adding the networking to the mix. Separating this not only has testing advantages, but also it means that you can, for example, if you have some sort of networking framework, you can plug it into that and let that manage the connections instead of net Postgres, which does the simplest thing possible. But like I said, net Postgres is an asynchronous Postgres module. Therefore, it's using promises all over. It starts even with making a connection, which is usually is usually a blocking action. In this case, it will turn a promise. If you await that, you can turn it into synchronous code. If you don't want it to be synchronous, you can plug it into something else. But more importantly, the queries are all asynchronous. Here you see an example. A simple query: select everything from foo where ID is 42. I think it should be obvious what it does. It looks very similar to what like DBPG does, except except for the promise. And actually, if you want to do it truly correctly, even the individual results are received asynchronously, and you can wait for every individual result as it comes in. However, in practice, once the result is done, once the query is done, the results will come in so quickly that I wouldn't usually do that. I would assume they would come in instantaneously, and just pretend that everything comes in one go. But it can also do a bunch of other things. For example, it can in this case, it takes it can convert the rows into like objects, because why not? It will take it as a hash and then use that as the constructor arguments, and then turn the rows into objects. It can do a bunch of things. But then I also mentioned types. Now, I explicitly wanted to have a very strong type support, because it's very useful for inflation. Type inflation is often done inside an ORM, because then the ORM has knowledge about, this column should be interpreted this way, and therefore it can do that. And in most database layers, you can't do that on a lower level. However, in Postgres, everything is typed. Every value knows its type. not just every column, every value, which is an important distinction. And therefore, you can actually inflate these values even if you're not using an ORM. Also, importantly, there's one way in which the type mapping approach of net Postgres is different from dbpq is that I make a distinction between type conversion and type mapping. Type conversion is literally how do I interpret this Postgres value to a Raku type? And the other way around, how do I turn this Raku type into a Postgres type? Whereas type mapping is the process of what type conversion am I going to use for this value in either direction. Essentially, type conversion is the how, and how do I do this, and the type mapping is the what. And this distinction is actually very important because that allows you to write easily write different type maps that will reuse the existing type conversions. By default, I define 3 different type maps depending on how magical you want things to work. But you can very easily write your own or use an existing one and then add your own conversions to that. But this dynamic nature is also important for some of the other type features. For example, type arrays. Postgres supports arrays of pretty much any type. And because I have this distinction, I can very easily, when you add a type, automatically also support the array type of it without any further effort, at least for the user. But it also allows me to easily support a bunch of other of the interesting types that Postgres offers. For example, enum types. I mean, I think we all know what enums are. Raku has enums, Postgres has enums. Why not map them to each other? In this case, I literally only have to tell it there's a Postgres type called ordering, and it maps to the Raku type order, and then it will automatically these two will be converted to each other wherever appropriate. And at least in my experience, enum types are actually fairly common, and this is a very useful feature. Another not very well-known feature in Postgres that should be better known are composite types. Composite types are kind of like tables and tables. They're a bit like structs. And they're useful for in a lot of cases where adding an extra table and joining that is an overkill. But you still want to be able to access the individual values. For example, you could define a type complex with a real part as a double and an imaginary part as a double. And like I said, no one would want to have to define a separate table to do this, but you also don't want to have some weird stringy format that you have to parse out manually. You just don't want to have to do that work. And this way, you can actually define that, and if you need to, you can actually access these individual parts in a query. And then, unlike our side, you can just define, hey, I have this Postgres type called complex, and I map it to the Raku type complex. And in this case, this particular case, I'm telling it the Raku complex type takes positional arguments, because by default I will use named arguments in constructors. It's just complex doesn't do that, so in this case I have to explicitly tell it. But in most cases you can just say map this to this, and then it will just magically work. And then lastly, there are domain types. Postgres domain types are very similar to subtypes in Raku. They're defined in terms of other types. They're not standalone types. They're defined in terms of other types, but they can have restrictions. You can say this is this other type, but it's not null, or it has to be larger than 3 or whatever. But there's one important distinction. It's a very important distinction from subtypes, because in Raku, subtypes values are not of the type of the subtype, whereas in Postgres they are. If you define a column as a certain domain type, it will know that it's the subtype, and if you fetch the value and you ask it what's the type of this value, it will give you the domain type and not the parent type. And this turns out to be very useful for an unexpected reason. You can use this for type inflation. For example, in my particular case, I would define a password type that's really just a string. However, the database knows it's a different type, and it will tell the client this value is actually of this domain type. And that means that you can use it to inflate it into something else. So, for example, in this case, I added a custom type passwords, and I say I'm mapping this to a crypt passphrase object, and then I tell it how to convert it, from that string into this crypt passphrase object. That should be smaller. Never mind. And these sorts of features mean that you can inflate a lot of values. Not necessarily. It can't be as specific as an ORM can be, because an ORM doesn't care about. Is able to not care about the database types. It can say this string is inflated this way and that string that way. But if you define the types specific enough, then you can use this to inflate any value and have like objects coming straight out of the database as if you're using an ORM. And I think that's amazing, because I do like getting like objects values, even if ORMs don't always do what I want them to do. Okay, but then there was the other type. Like I said, this module I wrote last year, and my big Raku module for this year was SQL Abstract, which addresses a very different part of databases. SQL Abstract is a way to describe SQL without typing the string, but using Raku data structures using Raku data structures to describe the query. I've already mentioned it a bit before, because my last presentation was essentially about the internals of this module, but I didn't actually describe well what it really does. And this is best shown with some examples, I think. In this particular here, I say select from my table columns bar baz, or select from my table columns bar baz where foo is 3. And it tries to be as intuitive as possible about all of these values. the columns and the conditions are the important ones. Well, actually, in practice, the conditions is the absolute heart of it, because that's I think you're going to use most. But it actually offers a lot of other options as well. For example, if I give it a pair, then I can say like, I want foo to be bigger than this value. I can ask it, I want foo to, I want the rows where foo are null. It'll even take junctions and interpret them sensibly, all 4 types of them, which I find a very, very useful feature, because it's actually very, very common to want to like, fetch, give me one of these IDs, and this will let you do that. But why would you want to do this? An abstract SQL implementation is not useful if your queries are static. Because if your queries are static, you might as well write them by hand. However, if you're like dynamically generating them, for example, like from you have a website and the user will tell you this field has to match that field will have to match that, then the abstract implementation will make your life a lot simpler, because you no longer have to compose your query yourself. And we all know how easily it is to mess up composing it yourself. This will allow you to compose queries in a safe manner. And safety is very important here. And the other part of that is, for this to be worth it, it has to expose as much functionality as possible, because it should not limit the programmer in what they're able to do in the database. It was an explicit goal of mine here to support all of the select, insert, update, and delete possibilities that are valid in both Postgres and SQLite, which are the 2 databases I personally care most about. It's also trying to support most of the things that are possible in Postgres that aren't legal in SQLite, but it will never be 100%, because you have no idea how much is possible in Postgres until you start implementing everything that's possible in Postgres. I have encountered corners that I didn't even know existed. Another reason why this was a fun project. But yes, it's trying to cover literally everything. Like joins are very obvious, but it's also like subqueries, window functions, which was something I hadn't actively used before. But now that I know what they are, I don't really understand how we did so long without them. And like conflict resolutions, when you're like inserting values, name anything you can think of and it will support that. And importantly, the other part of why you would want to use an SQL abstraction such as this is portability. Because the problem with creating your own queries is that there are always differences between the different database vendors. And the abstraction tries to hide these from you as much as possible. It can't fully do that. Also, because I'm focusing here on like inserting, manipulating data. I'm not focusing yet on defining tables, which is another can of worms where portability really goes out of the window. But as much as possible, I try to make it. I try to enable a programmer to just write what they want to do, and I will turn that into valid SQL for that specific database. I hope to support more databases than this in the future. However, I don't really have access to them, and a lot of them I don't care enough to do it myself. But if someone else writes it, then they're more than welcome to do so. This is another very important part of an SQL abstract. But then, of course, the real fun starts when combining these things. And this is where net Postgres async comes in, which is a module that it's actually a fairly small module that literally does this. It's instead of using a query method, you have a bunch of methods for all the different actions that will create these that will do the whole cycle of building SQL, a query, executing it, and returning you the results. For example, it can look something like this, like insert foo, insert into foo, the columns foo, these values, returning ID. I should have written what it resolves to. And this means that you can very easily write very powerful queries here without writing them by hand. And now I can hear you guys thinking, or at least I'm expecting this question. What about ORMs? This thing is not an ORM. And that has a reason. Like this is not like a competitor for red. This is more comparable to the layer underneath it, like the red AST. And I have been considering writing this. I might still write it some other day, but it turns out to be actually the ORMs are very difficult to write, and this has a reason. Because fundamentally, the object model and the relational module have a huge impedance mismatch. It's very hard to translate a lot of these concepts. And because of that mismatch, ORMs are inherently, all of them, very, very leaky abstractions. All of them. I think Larry Wall once famously paraphrased. He was paraphrasing Alan Kay when he said, "Easy things should be easy, and hard things should be possible." And I think this very accurately sums up the difficulty in ORMs. It is very difficult to do both. Almost all ORMs are focusing on the first part. Like most ORMs are brilliant, and Red is a good example of that. It's absolutely brilliant at making easy things easy, but there comes a point when you're writing, when your queries are so complicated that you can't express them in an object way. And that is where writing they become difficult. And to be entirely honest here, I wouldn't have written this if I didn't like databases. I really like the whole relational model. And to be honest, I think if I would write something like this, it would be a lot more DBIX class-like. Not entirely, but something like that. But I'm not smart enough to write an ORM that I do like. That, I think, sums up the problem. But maybe next year, when I sent this, I was like, can I write something before that time? The answer is no. But yes, I think it is possible. It would be interesting to try this. but it's very difficult. I think this was my last slide. Are there any questions?
It's not, I have not so much of a question, but a suggestion. I'll be very interested if I see more examples with verbal descriptions of your translations, because it's hard for me to get oriented in this, right? And to some extent to take your perspective, but I would like to address it through domain-specific languages from natural text to generate code, which uses, say, your package. And in order to do that, it's I'm not sure when I was presenting, but for example, the documentation list made for AppRack, right? It can be very instructive in that way, because I can first read it, but even if I don't read it, I can make some automatic translation with it to begin with, right? And so I can actually speed up the whole process. I mean, I'm a little bit probably talking to abstract here, but the question is that, yeah, some kind of documentation how you verbalize certain workflows with the SQL, right? And they get mapped into this SQL abstract design. It's very useful.
Yes, that's the it's I could have added more examples, I suppose, but it's also there are so many. Choosing the right examples is actually the hard part here. Like, there are many things it can do, and some of them are kind of obscure and some of them are common, and I tried to show a few common ones, but I guess the obscure ones may be more interesting. But yeah, fair point.
I don't see a raise hand option, so I'll just talk. A question I'd asked earlier, do you have any, I know about hypothetical, but do you have any numbers yet, like about how this performs asynchronously compared to the other version?
I haven't actually measured it. And I also think it's very hard. I'm looking for the right words. I mean, the synchronous version is essentially underneath written in C. So in terms of raw throughput, it should be much faster. Absolutely. However, in a lot of cases, that is not your bottleneck. Because in a lot of cases, you're waiting on a database. You're spending far more time waiting on a database than, like serializing things and stuff.
I was thinking more in terms of like the time from beginning to end to process a request that may redo several things. Like the higher level thing, like for example, do you get something that used to run in 5 seconds complete in 1 or something because it's concurrent, or have you measured anything like that?
I haven't measured anything like that, and in practice, this is going to depend entirely on your specific case. Like doing things asynchronously is advantageous if you're actually using that to write concurrent codes. If you're like, in a lot of cases, if you're just writing a script that pumps data into a database or something, then there's not much of a point to make it asynchronous. But if you're writing like this web application that's handling a lot of different connections and just send out query and then switch to handling another client, then it can be much faster. It depends too much on the specific use case.
Well, I guess the question is, for your use case, did it actually help you so far, making it faster for what you do?
I haven't tested that quite yet because I'm not done with where I want to be. You know, this is really like all of this is really a long-term process, a long-term project. But yeah, you have a point. I should have measured this. Yes. Anyone else? I'm not sure if this is good or bad that so few people have questions.
I'm happy to talk about a lot of things related to this, but I didn't want to monopolize it. I wrote a bunch into the chat.
I'll have a look at it. Well, and if there are no more questions, then I am done, and the next speaker can come up.